Hello, can you hear me?
Yes, ma'am.
Okay. So yesterday we had discussed some properties of principal components. We derived their variance, covariance, and we also saw how to decide how many principal components should be retained in the further analysis. And um, we also saw how to compute scores. Okay, so today we are going to focus on actual applications of principal component analysis. While discussing the need, we had listed three applications. First one among them was dimension reduction. Correct? So part of this we discussed yesterday, that if I have p variables, ideally from those p variables I actually get p principal components, but we do not retain all p. We use either the scree plot or the percentage variation explained. So we used either the scree plot or the percentage variation explained to decide out of these PPCs how many should be retained. Okay, and that number we try to keep as small as possible. What is the advantage of that? Of course, first advantage is computationally dealing with less number of variables is more helpful. You require less memory for all the computations, and secondly, if you can reduce that number to say 2 or 3, then plotting becomes very easy. Okay, plotting or visualization is easy, and visualization can help you find many patterns, right? So this is one type of dimension reduction. But some of you might have realized that at the data collection level, this still needs all the p variables, because when I say I have some equation for PC1, we know that equation looks like L11x1 L12x2 plus L1p Similarly, PC2 is L21x1 L22x2 plus L2p. When I say this, it means that even if I decide that okay, I'm going to work only with two PCs, for computing those PCs I need x1, x2, xp, everything. Okay, so at the data collection level or at the data storage level, my efforts are still not reduced. I am still in the same dimension, that is n cross p, original data. Okay, for score plot etc. I might be using less number of variables, less number of principal components, but for computing those PCs I need entire n cross p data. Hence, some people feel that this is not really dimension reduction, this is kind of pseudo reduction. Okay, so can we do some sort of real dimension reduction? Means, can we throw some variables from the initial data and work with less variables? So that can also be achieved up to some extent with the help of these equations. So what do we do in such cases? We try to see these coefficients. Okay, and generally coefficients which are large in magnitude, they tell me that okay, for example, if in PC1, if suppose magnitude wise this is the largest coefficient, okay, just an example, then that means that in PC1 role of second variable is quite large, okay, quite important. So then I would say that probably second variable is one of the important variables. There is a small problem in this argument. Okay, we have to understand things more in a more detailed manner. What is the problem? If my xi's are in different units, then unit of xi's is also going to affect my coefficients, that is L11, L12, etc. Okay, so if say x1 is in centimeters and x2 is in kilograms, then L12 might be small, but that doesn't necessarily mean that x2 has less impact on PC1. Okay, so whatever I said about impact should not be taken directly at the face value. Generally, yes, the coefficient, magnitude of the coefficient does denote something about importance of that particular variable in that particular PC, but it doesn't give me complete picture because it is not unit free. In fact, that actually leads us to another problem. If I am saying x1 is in meters and x2 is in kilogram, does this equation even make sense? Because I am adding something in meters to something in kilogram, which is not really allowed under the laws of physics. You cannot add meters to kilogram. Okay, so what can we do in such cases? Is there any way in which we can make variables unit free? In statistics, is there any way in which we can make variables unit free? Any quantity which is which does not depend on unit of the variables? Am I connected?
Standardizing random variable.
Standardizing, correct. So what do you do in standardizing? What do you do when you say you are standardizing a variable? Anyone can answer. It doesn't have to come from the same person. When you say you are standardizing a variable, what do you actually do? Yes? Nobody knows?
No, we calculate the variance.
And what do you do with that calculated value? Anyone?
We subtract the mean and divide by standard deviation.
Correct. Okay, so fine, standardizing. So when you standardize variables and if you compute their covariance, what does it give us? Covariance of standardized variable, does it have some name in statistics? Covariance of standardized variables, does it have some name? No? Covariance of, say, x minus mu x upon sigma x and y minus mu y upon sigma y. Does it have any other name in statistics?
Correlation.
This is exactly same as correlation between x, y, correct? If you are not sure, try this as homework. Okay, this is homework. Covariance between x minus mu x upon sigma x and y minus mu y upon sigma y, where x, y, everything is scalar, is same as correlation between x, y. Okay. So, whenever we have variables in different units, ideally, instead of using sigma x and computing its eigenvalues, we should use correlation matrix. Okay. We should use correlation matrix and then compute eigenvectors and eigenvalues corresponding to correlation matrix instead of covariance matrix. Is it okay so far? Okay, so let me go back to my question. So if now I'm making sure that my variables are in same unit, then the coefficient here L11, L12, etc. can indicate the extent up to which these variables affect PCs. And we know that PC1 is most important. So whichever variable has the largest effect on PC1 can be considered as most important variable among the original variables. Okay. So then we look at the coefficients, and whichever coefficient is largest as per magnitude, we take that variable as the most important variable. Then we go to PC2. Okay, so from PC1 we try to identify generally only one variable. Then we go to PC2 and we try to see which variable is, and we of course skip the first variable that is already there and we consider the second variable, and then that becomes second important variable, and so on. So this way, if I have decided to retain k PCs, I might be able to get somewhere around k important variables. I'm not saying exactly k, because sometimes in some PCs more than one variable may be having almost equal impact. So we may have to consider more variables. Okay. But this is dimension reduction in true sense, because if you do this PCA exercise on say some pilot data, and if you identify some important variables, then later while collecting the entire actual data, you may not even collect data on all p variables. You may collect data only on k variables and still you may not lose much. So in that sense, this is true dimension reduction, because you don't really have to collect or store data on all p variables. Okay so far? So this is how dimension reduction in PCA works. You look at the coefficients and identify the important variables. Second application of PCA was unsupervised classification. Okay, what do I mean by unsupervised classification? We yesterday computed scores, correct? Those scores can be plotted. So scores corresponding to PC1 and scores corresponding to PC2. We can draw a bivariate score plot. Okay. And suppose that plot shows some natural clusters or natural groups. If that happens, then I can try to see if these groups represent something. Okay. If these groups represent some cause of variation, and then when a new observation comes, I can try to compute its score using whatever equations for PCs I already have, and then I can try to see where that new observation is located. If suppose it is located here, then I will say it is of this particular type. If I can, give some name to that type, then I will say okay, it is this particular type. I think initially in the earlier lectures I gave you some example of paper wasps, right? So in ecology, people studied paper wasps, and just like honeybees, paper wasps also have different categories: queen wasp, and then workers and males, etc. So you could, when people collected data on their physical characteristics like head length, head width, body width, etc., leg length, etc., then they could see such three groups in the PCs, in the score plot. Of course, when you have 10 variate data, you cannot see patterns in all those 10 variables simultaneously. But PCA helps you in extracting those patterns in a more, what we would call more insightful way, because it extracts variation most, and hence it can discover some patterns which may not be visible in the individual variables, But because principal components are chosen in such a way that they maximize variation, they might be able to give us such groups if such groups are naturally present in the data. We will also see one example where we try to classify currency notes, whether they are fake or genuine, using PCA. So there also we will clearly see such two groups, and then after seeing the two groups, we realize that okay, first group corresponds to fake notes and the second group corresponds to real or genuine notes. Okay, but remember, I am calling this as unsupervised classification. Why? Because while computing scores or while doing PCA, we have not used the information about groups. Okay, we might have it with us. So for example, as I said, in the currency note data, I already know that first 100 notes are of one type and rest 100 notes are of another type. But while doing PCA, we do not use that information. We treat all 200 notes as one single group. We carry out one single principal component analysis on all these 200 notes, and then in the score plot we see there are two groups, and then we go and check which observations are in one group, and then we realize that oh, all the observations in group 1 are from fake notes, all the observations in group 2 are genuine notes, either all or most of them. Then we say that okay, so probably PCA could be used for distinguishing between fake notes and genuine notes. Okay, there is a chance that PCA could be used for distinguishing between fake notes and genuine notes. So it is called unsupervised because while we did not use the information on the group while drawing the score plot up to that stage, even for getting groups. After getting the groups in this picture, we try to see okay, this group belongs to certain category or not, this group belongs to certain category or not. But up to computation of scores, we did not use any information about the grouping structure. Is it clear how PCA can be used for unsupervised classification? Yes or no?
Yes, ma'am.
And the third application that we discussed was principal component regression. So what is this? You are studying regression in the current semester. Have you already heard the term multicollinearity? Have you heard the term multicollinearity in regression? Yes.
No, ma'am.
You have not heard the term multicollinearity in regression class yet?
No, ma'am.
Okay, fine. So let me explain. So what is multicollinearity? When you are having multiple regression setup, you have one response y and you have suppose x1, x2, xp as the p regressors. Okay. So this is my response. Sometimes what happens is these regressors may be correlated with each other. Okay. So there may be high correlation among themselves. A very classic example is if you are trying to predict height of a child using height of parents, then height of parents is quite likely to be correlated because generally people tend to marry, taller people tend to marry taller people. So height of parents can be correlated, and then these correlations can sometimes cause problems. Why? You have studied multiple regression, right? Did you derive formula for variance of beta hat in multiple regression?
Yes.
What is the formula? Does anyone remember? Or you can check your notes, I don't mind. What is the formula for variance of beta hat? Sigma square into something. Sigma square into what?
X transpose X inverse.
Correct. X prime X inverse, where X is a what we call it, design matrix. What do you call it? Design matrix or regressor matrix? What do you call?
Okay.
Okay, so X prime X is kind of like covariance, right? Because your covariance is expectation of in general, your covariance is expectation of xy minus expected x into expected y, univariate setup, right? So this x prime x is kind of like covariance matrix. So if correlations are high, then this x prime x matrix is nearly singular. Okay, rank of x prime x is rank won't be exactly affected because I am not saying there is perfect correlation, but x prime x will be nearly singular matrix. Why nearly singular? Because every column of x, original x matrix, every column represents one variable. So if multiple variables are correlated, then in x prime x, your independence is kind of lost. Independence between variables is reduced. As a result, some of the eigenvalues become almost close to 0. Because you know that if all the rows and columns are independent of each other, then it's a full rank matrix. If some rows or columns become linearly dependent on other, then the rank gets reduced. This much everyone knows from linear algebra, that if one row is say linear combination or multiple of some other rows, then the rank is reduced.
Yes, ma'am.
Okay, so if my variables are highly correlated, linearly correlated, then rank of x prime x, if they are perfectly correlated, then rank would reduce. But even if they are not perfectly correlated, if there is some partial dependence on them, then x prime x, the determinant becomes close to 0 because some of the eigenvalues become very low, and we discussed yesterday also that determinant is product of the eigenvalues. So this becomes nearly singular. If x prime x becomes nearly singular, then it means that determinant of x prime x is quite close to 0. If it is quite close to 0, then when I am computing inverse, in inverse, does determinant come in picture? Inverse of any matrix. A inverse is, you have some formula involving determinant, right? In linear algebra. What is that formula?
One upon A inverse into adjoint of A.
1 upon determinant of A into adjoint of A. Correct. So determinant is in the denominator. So if determinant is almost 0, then A inverse gets very high values, because you are dividing by 0 means you are going towards infinity. Are you following whatever is happening here?
Yes, ma'am.
So A inverse becomes very high. So if x prime x is nearly singular, then x prime x inverse gets inflated. As a result, variance of beta hat gets inflated. So now my estimates have very high variance. Very high variance means they become unreliable, because variance is high means whatever estimate I have computed, I am not very sure about this. Spread is quite high. Even if I give confidence interval, that confidence interval will be very wide. So my confidence in my estimation gets reduced, and hence it causes problems. Okay. So this entire issue is known as multicollinearity. Okay. In multiple linear regression, if the regressors are highly correlated among themselves, then that leads to inflation of variance of the estimated coefficients, estimated betas, because of this explanation. And as a result, our confidence in estimation reduces, so our estimation is not reliable, and that is known as multicollinearity issue. So there are various methods by which you can deal with this multicollinearity. One of the methods is what is known as ridge regression. You will see that in your regression course in detail. So ridge regression is one of the methods. We are not going to go into that because that has nothing to do with PCA. So how does PCA help in multicollinearity setup? See, the problem is because the regressors are highly correlated with each other. Okay. So if I can reduce the correlation, then that helps. And that is exactly what principal components are going to do. Principal components are orthogonal to each other. They have no correlation among themselves. So instead of using x1, x2, xp, if I compute PC1, PC2, PCP, then correlation is actually 0 among these species. And now with y as response and these guys as regressors instead of x1, x2, xp, I can carry out the regression analysis more confidently, and that is known as principal component regression. So when I say I use PC1, PC2, PCP, I basically use the score matrix. So first column of score matrix is corresponding to PC1 values for all the observation. Second column of score matrix corresponds to PC2 values of all the observations, and so on. So we use these as regressors and response stays the same, and then multicollinearity issue is gone. Okay. So this is known as principal component regression. Of course, no method is perfect, so this has its own problem. And one important problem is, if I had original variables x1, x2, xp, then interpretation is easier. For example, I said y could be kid's height and x1 could be say mother's height, x2 could be father's height. Then when I get coefficients beta 1, beta 2, I can say that okay, father's height has this much effect on kid's height, mother's height has this much effect on kid's height. I can compare which is large, which is small, etc. Whereas if I use PC1, PC2, PCP, every PC is going to be a mixture of all the xi's. So I cannot really understand what is the effect of individual original variables, because PCs themselves may not have any interpretation. Okay, PCs themselves may not have any interpretation. So understanding the relationship between variables in regression becomes difficult. But if your aim is purely prediction, if you are not too much bothered by how you or why you get a particular prediction, if your aim is just prediction accuracy, then principal component regression will give you better results than usual regression if there is multicollinearity. Okay, if there is a multicollinearity issue. How to detect multicollinearity, etc., means how to decide whether multicollinearity is present or not, etc., you will discuss in detail in your regression course. Okay. Okay. Now let me, so these are three major applications. For, as I said, classification and dimension reduction are most important. So for those applications, we also use something known as biplot. Okay. So what is a biplot? Biplot is actually, as the name suggests, plot of two things. First is of course observations. Okay. Whatever observations you have. Sometimes you may have clusters, sometimes you may not have clusters, etc. And in addition to observation, so these observations are actually plotted as scores. But in addition to that, you also have variables in the form of arrows. Okay. Variables are plotted in the form of arrows. Okay. So you may have x1 here, x2 here, x3 here, and x4 here. Okay. So your variable arrows may have different lengths or you may have same length, etc. So what are the interpretations of biplot? First of all, if there are any natural classes which could be observed in score plot, those could be observed via biplot also. So natural classes or clusters present in the observation can be obtained via biplot. Secondly, if there is any grouping in the variables, then that is also evident from the biplot. So generally, acute angle between arrows indicates strong positive correlation between corresponding variables. Okay, acute angles indicate strong positive correlations, So obviously obtuse angles indicate strong negative correlation. Okay. Acute angle indicates strong positive correlation. Obtuse angle indicates strong negative correlation. And angle around 90 degree like this indicates no correlation. Generally, okay, this is, I mean, we shouldn't conclude purely on the basis of plot, but it is more or less the case. Acute angle indicates strong positive correlation. Obtuse angle indicates strong negative correlation. And orthogonal relationship indicates no correlation. Further, length of the arrow is proportional to variance of the individual variables. Okay, length of the arrow is proportional to variance of the individual variables. So variables which have high variance will have longer lengths. Okay, and variables which are very close to each other, because angle is less, they are kind of like grouping together. Okay, so grouping between variables can also be seen. Grouping among observations can of course be seen via biplot. And there is one more important thing. So for example, I have such three groups which I have indicated here. So we can see that this group, the arrows for x3 and x5 are kind of directed towards this group, whereas x1, the back of x1 is towards this group, or whatever this was, x4. So this particular group is on the opposite side of x4. Okay, so now x5 and x3 are directed towards this group would mean that this particular group has higher values of x3, x5 compared to say this group which is on the opposite side. Let me repeat what I said. This particular group has arrows of x3 and x5 directed towards it. So observations belonging to this group will have higher values of x3 and x5 as compared to observations on the opposite side. Okay, so observations which are towards the direction of the arrow, they have higher values of those particular variables, and the observations on the opposite side have lower values of those particular variables. Is it okay? How to plot these arrows, how to get these coordinates of these points, etc., we are not going to go in detail, but this is done via your singular value decomposition. Okay, so it could be proved mathematically how it happens, but we won't go into that detail. We'll focus on the interpretation. So this biplot is another thing which would help us in applying PCA to real data. So score plot, biplot, the coefficients in the PC equation, these all could be used for interpretation. There is one more thing which could be used for application and interpretation, but I am not going to derive the formula. Deriving the formula is homework. So correlation between PCs and original variables. Okay, so correlation of say jth PC with ith variable, this is homework. Okay, you have to derive this at home, and this correlation can also be used in interpretation. So if a correlation of a particular variable with a particular PC is high, it means that variable has a good role in deciding the value of that particular PC. Is it okay? Did you get what I said just now?
Ma'am, can you repeat once?
If correlation between say jth PC and ith variable is very high, either positive or negative, either direction, then I would say ith variable has an important role in jth PC, or ith variable has high impact on jth PC. So ideally, instead of simply relying on coefficients, we should compute correlations of all PCs with all variables and then use those for deciding which variables are important, which variables should be retained while doing dimension reduction. Is it okay? Is it okay? Is it clear?
Yes, ma'am.
Okay. So these are applications of principal component analysis. In the next lecture, we will see some real case studies where PCA can be used. We will use some known data or some textbook data. And we will also see R commands for principal component analysis. But generally, I suggest people that in this semester, in the current semester, you should not use built-in R commands. You should use eigenvalue, eigenvector. You can compute using R. I mean, you can use direct command for eigenanalysis. But after that, computation of scores, etc., should be done by writing codes on your own, because that helps you more in understanding the technique. Okay, writing code is more helpful than using the direct command. Okay, in the next semester, so in third semester assignments or in fourth semester project, if you decide to use PCA, if you feel the need to use PCA, then there you can use the direct commands available in R. But here I generally suggest that in second semester, try to avoid direct machine learning commands. Okay, is it okay?
Yes, ma'am.
Okay, so let me stop here for today. We will continue with the applications and case studies in the next lecture. Thank you.